Good morning to one and all. I am Dr.I.Diana Jeba Jingle, and I am working as Assistant Professor in School of Engineering and Technology, Christ University, Bangalore. And I thank the management for providing me an opportunity to present in this webinar. And in this webinar, I am going to talk about quantum computing and its applications. What is quantum computing? So the quantum computing is an area of study and it is focused on developing computer technology based on the principles of quantum theory on a quantum level. So what is quantum level? Quantum level consists of atomic and subatomic levels. And atomic in the sense, a particle that cannot be divisible further can be called as atomic particles. So these quantum computing, this quantum computing principle is based on quantum theory that works on small particles, atomic particles. And quantum theory explains the nature and behavior of energy and particles. So what is quantum theory? So inventors and researchers, they have developed some theory in the past, and these theory were followed by quantum computing concepts. And what is the theory? The theory tells us that is energy was made up of individual units or quanta. And not only energy, radiation, that means waves also, it will be quantized and in the same manner as energy. Energy consists of discrete units, and that means the energy is not continuous. The elementary particles of energy depending upon the conditions, may behave like either particles or waves. So there is a theory called as wave-particle duality. So what does this theory tell? The movement of elementary particles is inherently random and it cannot be predicted because of this nature. And another one theory is that is uncertainty principle. So this principle tells that simultaneously measurements, when you measure two complementary values like position and momentum, when you are trying to measure both position and momentum of a particular system simultaneously, it is impossible. So only one will succeed, only one measurement will succeed. So the more precisely one value is, the more flawed will be the measurement of the other value. And so we will, I'll be defining what is qubits. I will be sharing you the definition of what is qubits. Qubit is also called as quantum bit, and it is a two-level system where each state of a system is a quantum state. So qubit is the fundamental building block of a quantum information. So there are two types of systems, that is, one is classical system and the second one is quantum system. So classical system, normally we represent a classical system in the form of bits. And bits consist of 0 and 1 symbols. Quantum system can be represented in the form of ket 0 and ket 1 symbols. And here, quantum systems are measured as qubits and they are represented as ket 0 and ket 1. So this notation, that is the last point, I have used a notation called as Dirac notation. So this notation is also called as ket, that is used for describing qubits symbols. So what is the difference between bits and qubits? Consider a system, that is, or a coin, we can tell. Consider, for example, a coin. A coin is flipped in the air. So when it reaches the land, you will be observing either a head or a tail. So if you observe a head, the value will be 1, and if you observe a tail, the value will be 0. So at a particular time when you observe, only one value, that is either head or tail, will be measured. So simultaneously both zeros and ones cannot be possible in a classical system. But in a quantum system, consider the same coin is flipped in the open mid-air. So what happens? Assume the position of the particular coin is in some position, that is when you observe that particular coin in mid-air, half of the time, that is, it will be in position, not half, we can tell. Uh, the coin will be in position tail at with probability, with some probability, and it will be in position head with some probability. So if the coin is in facing the head with some probability, then you will be telling the value as get one with some probability. If the coin is facing and the tail, when you observe, so then you'll be denoting it as ket 0 with some probability. So simultaneously both ket 0 and ket 1 will appear, can be observed in a system. So this type of system we'll call it as quantum system. So quantum computing has its growth for the past 20 years, starting from 1998 till 2019. And IBM, companies like IBM, Oxford, Berkeley, Stanford, MIT jointly developed a 2-qubit quantum system in the year 1998. And then Technical University of Munich developed a 5-qubit quantum system in the year 2000. Los Alamos National Laboratory developed a 7-qubit quantum system in the year 2000. The Institute of Quantum Computing, along with MIT, developed a 12-qubit quantum system in the year 2006. Then D-Wave Systems developed a 28-bit quantum computer in the year 2008. Then again, IBM, Oxford, Berkeley, Stanford, and MIT jointly created a 50-qubit quantum system in the year 2017. Then Intel created a 49-qubit quantum system in the year 2018, and Google has developed a 72-qubit quantum system in the year 2018, and Rigetti has promised to develop a 128-qubit quantum system in the year 2019, and still it is under progress. So quantum computing has its evolution from 1960s, and it has evolved till 2020, and there's a lot of scope for quantum computing in the future. So in 1960, a researcher developed a conjugate coding theorem. So this coding theorem is based on the concepts of quantum computing. And in 1970s, in the timeline 1970s, so the researchers developed a non-cloning theorem, Olivo's theorem, superposition principle, quantum information theory. All these theories are based on quantum computing concepts. Then in the time 1980s, Turing machine, Toffoli gates. So Toffoli gate is a reversible gate. So that is most commonly used for quantum computing operations. And then universal quantum computer. So all these machines were developed in the 1980s. Then in 1990s, the entanglement property, factorization algorithm, quantum cryptography, quantum error correction, quantum database search algorithms, quantum annealing. These are the different methods and algorithms and concepts were developed in the 1990s. And quantum node deleting theorem, optical quantum computing, these are the concepts that were developed in 2000s, in the time 2000s. And in 2005, the first quantum byte, also called as qubit. So 1 qubit is equal to 8 qubits, similar to 1 byte is equal to 8 bits. Then in the year 2006, in the time 2006, quantum bang error correction algorithm was developed. Then in the time 2007, a 28 qubit quantum annealing computer is a different type of quantum computer was developed. Then in the year 2008, quantum RAM and 3D quantum Qubit chips were developed. And in the time 2011 to 2015, quantum antennas, quantum repeater system, quantum factoring algorithms were developed. Then in the time 2016 to 2019, ion trap based quantum computer, Q-Sharp, 72-bit Bristol cone chip, IBM Q System 1. These are the different quantum computers that were developed in 2016 to 2019 time. And currently, 2020, got qubits, where it is a type of qubit that is under process. So there are some companies that are using quantum computing and that they are providing service for providing cloud service for computing algorithms, for executing quantum computing algorithms. So Google, first of all, the first company that is very much that is providing quantum computing services to the users is Google. It has developed a 72-qubit D-wave quantum computer, and this computer is used for cryptographic research. Then secondly, Microsoft has developed an open source Q-Short compiler language as well as simulator tool that is, and they have used it for engineering the quantum states. Then thirdly, IBM has developed a 50-qubit IBM Q quantum computer that is used for commercial quantum research. Then next, Intel has developed a 49-qubit Tangle Lake quantum computer that is used for evaluating quantum computers. It is a testing tool that is used to evaluate the quantum computers. Then Toshiba, it's a company that has developed a 5 quantum distribution device, and mainly for maintaining the security of data. NTT has developed photons chip cold quantum computing chips. These for providing encryption and precision medicine. Then Honeywell has developed a trapped ion quantum computing, and this computing it's ongoing. This work is ongoing, and it has been considered as a research project, funded research project. And D-Wave Solutions has developed a Leap quantum cloud service that offers real-time access of this quantum devices, in the quantum resources in the cloud. Alibaba has developed a cloud-based quantum computing service for performing artificial intelligence, e-commerce, and also security purposes. Then Lockheed Martin has developed the USC Lockheed Martin Center for Quantum Computation, and Lockheed has developed this thing for manufacturing and aircraft design logistics. To control the aircraft machines, they have developed this quantum computer. So these are the top 10 companies that are using quantum computers, and quantum computers are evolving, and quantum algorithms are emerging with for providing some many types of providing solutions for many types of problems, hard problems. So I already told you the difference between bits and qubits. So a qubit is a quantum state of a system that has both Ket0 and Ket1 simultaneously. So a qubit, a system in a quantum state is a combination of Ket0s and Ket1s with different probabilities. So there is a chance for both the states, both Ket0 and Ket1, to appear simultaneously in the system with the different probabilities. But this thing we cannot tell in terms of bits. So what is a quantum state? A quantum state is a unit vector in a two-dimensional complex vector space. So unit vector means a vector whose magnitude is 1, we'll call it as unit vector. So these quantum states have real, experimentally verifiable consequences, and they are essential to the power of quantum computation and quantum information. The quantum states are very fragile because of its tiny size, because they are very tiny, they are atomic particles, and they have very low energy levels. And because of this, because of their very low energy, these states are not permanent and they may fade at any time. So the interaction of these states with the environment, we'll call it as decoherence property. So when a quantum system um, in a particular state interacts with the environment to produce a new state. So the new state will be having will not be similar to the previous state. It will be having some mixture of noise. That is because it is interacting with the environment. So this property is called as decoherence property. A qubit can exist in a continuum of states, as I told you, between ket 0 and ket 1 until it is observed. So more precisely, a quantum state is a superposition of 0 and 1 states called as qubit. So this is how we'll be representing a quantum state. That is, ket psi is a system that is having ket 0, state ket 0 with probability alpha and state ket 1 with probability beta. For example, this is a coin, that is a system. So in a particular state, this coin is in position when you observe. It is in position, tail position with probability alpha and head position with probability beta. So simultaneously, both the tail and head can occur with different probabilities. So this ket alpha and beta are all complex numbers. They are used for denoting the probabilities of the occurrence of this particular states. So there are two types of quantum states. The first one is the single qubit state, and the next one is the multiple qubit state. Single qubit state. So in a single qubit state, only one, either ket 0 will be there or ket 1 will be there. Only one state. A single qubit state consists of either ket 0 or ket 1. So ket 0 will be having two states. We can represent either ket 0 or ket 1 in the form of two values. So a single qubit state is a superposition of linear combinations of zeros and one states. So this is the representation of a single qubit state. Ket psi is equal to alpha ket 0 plus beta ket 1. A state, that is, suppose this is the state 0, initial state. Normally we will represent an initial state as ket 0. So assume it is ket 0 is equal to, you will be getting a, when you ket 0 is a, consider ket 0 is a coin. So when you flip that coin will be in tail position. So tail position with probability alpha and head position with probability beta. So this condition, that is this is the representation of quantum system, and the condition is alpha square plus beta square is must be equal to 1, and alpha and beta are complex numbers. So this is the matrix representation. How will you represent a ket 1 in matrix form? So ket 1 is represented as 0, 1, and ket 0 is represented as 1, 0 in matrix. And so here, if alpha square is equal to 1 and beta square is equal to 0, then ket psi is equal to 0. If alpha square is equal to 0 and beta square is equal to 1, then ket psi is equal to 1. If alpha square is equal to 1 by 2, that is 50%, and beta square is equal to 1 by 2, that is 50%, then ket psi is equal to half 1 by root 2 because it is alpha square. So alpha means root 1 by 2 will be converted to 1 by root 2. 1 by root 2 ket 0 plus or minus 1 by root 2 ket 1. So this is how we will represent a single qubit state. Then the next thing is a multiple qubit state. A multiple qubit state is a superposition of linear combinations of different qubit states. That is, a multiple qubit state will be having more than one qubits. So consider a two qubit system. More than one, two and more than two, we'll call it as a multiple qubit state, a qubit system. So consider a two qubit system. So how will you represent a two qubit system? Consider, assume that you are having 0 and 1. Assume this is a two qubit system, 0, 1. So how will you represent this system? This system can be represented represented as 4 values. This system will be having 4 values. How? 2 power q is equal to 4. In this n is equal to if n is equal to 2, then 2 power n is equal to 4. So that is why a 2 qubit system will be having and represented in 4 different ways. So in consider the ket psi. Ket psi is a 2 qubit system. So ket psi is having 4 values. How will you represent these 4 values? That is alpha 00 ket 00 plus alpha 01 ket 01 plus alpha 10 ket 10 plus alpha 11 ket 11, where alpha are all complex numbers that are used to represent the probability of this state. So the meaning is ket 00 will be in this state with probability alpha 00. Ket 01 will be in this state with probability alpha 01. So when you take the summation of all these alphas, all these probabilities, its value should be equal to 1. So that is the concept, that is the rule, mathematical rule. So here I have given summation x belongs to curly braces 0, 1 the whole square. So these are the 2 states that a 2 qubit system has. A 2 qubit system has 0 and 1 state altogether. Okay, so these 0 and 1 state can be represented and will be having 4 different values. So that's what it has represented like this. And an example for 2 qubit system is Bell state. So you might have learned in linear algebra what is a Bell state. So a Bell state will be having ket 00 plus ket 11 divided by root 2. System in this state we'll call it as a Bell state. Then now we'll go on to the properties of quantum computing. Properties of quantum computing. Quantum computing consists of 3 different properties. These properties play a major role in quantum computing. And superposition, entanglement, and interference. So what is superposition property? It is the ability of a quantum system to be in multiple states simultaneously. So a quantum system will be having many states, and these states can occur simultaneously with different probabilities. So this property is called as this superposition property. Example, flip of a coin. As I already told you this example. When you flip a coin, if you look this coin in binary form, binary concept, the coin will be having either binary 1 or binary 0. That is either head or tail. So when it lands, when the coin lands, it will be showing either a head or a 0. So both head and 0 cannot appear simultaneously. But consider the same coin when it is in the mid-air. So it is having both head and tail with different probabilities. So both head and tail can occur simultaneously with a different probability. So thus the coin can exist simultaneously in 2 states unless the operation of measurement is made. So when you see it, you can see 2 different states. But while you come for measurement, when you measure, only 1 state will succeed. So this is the main concept of superposition property. So only observables can be measured. Whatever you observe, it will be measured. So that is, if a tail is observed during measurement, then the state of the coin is at 0 with some probability. So this is an example for superposition. So a classical state, when you flip the coin, you will be getting either a head or a tail. So if you are getting head, the value will be binary value will be 1. If you are getting tail, the binary value will be 0. So either 1 or 0 will be occurring, but both head and tail cannot occur simultaneously. But in a quantum state, consider the same coin in mid-air. So both, assume this is the position of the coin in the mid-air. So in this diagram itself, you'll know that the coin is facing, that is, you can observe head with some probability and tail with some probability. So here I have taken like a head with the probability 1/2 and tail with probability 1 by 2. So how will you represent this this state, this quantum state in as a quantum system? Ket psi is equal to 1 by 2, alpha is 1 by 2, ket 0 and 1 by 2 plus 1 by 2, ket 1. So the coin is assumed to be in both states simultaneously. So this property is called a superposition property. Now we'll go on to entanglement property. So this quantum property takes objects and connects them by permanently entangling them together. So assume a 50 qubit quantum machine. So this 50 qubit quantum machine can be expressed, will be having 2 power 50 quantum states simultaneously. So we can represent a 50 qubit quantum machine in 2 power 50 different states, and these states can occur simultaneously. So in the same way, consider another 150 qubit quantum machine. So and represent that machine also in 2 power 50 different states. So what happens is any one of this particular 2 power 50 out of 2 power 50, any one of this particular state will be having a match with the next system, will be matching the states of another one quantum system. So this property is called as entanglement property. So the increase in power plus the entanglement of qubits allows quantum computers to solve problems effectively. So this is the main feature of quantum property. If you find the solution for suppose if you are finding a solution for one of 2 power 50 states, one state of 2 power 50 state, there is a possibility to find a solution for the another system, for the next 50 qubit quantum system with for any one of its states. So I'll show you with an example. Consider 2 coins. In superposition, we learned with one single coin, but in entanglement example, I will show you with 2 different coins. Consider 2 coins that are flipped simultaneously. So this is one coin that is flipped simultaneously, another one coin is flipped. So this coin, when flipped, you will be getting 2 values, that is alpha 1, the head with probability alpha 1, tail with probability beta 1. Similarly, you have flipped another one coin. That coin is having tail with probability alpha 2, and head with probability alpha 2, and tail with probability beta 2. So assume like this, there are many more coins that you are flipping, many coins, some thousands of coins you are flipping. So at a particular time or state, any one of this particular coin's state will be matching with this particular coin's state. This property is called as entanglement property. So I have to represent these 2 systems as a quantum system. Ket psi is equal to alpha 1, beta 1, ket alpha 1, ket beta 1 plus ket alpha 2, ket beta 2. Suppose if you find a solution, suppose if you want to find the value of alpha 1 and you got the value of alpha 1, so there is a possibility of to easily find the value of alpha 2 also, to easily find the value of alpha 2. So this property is called as entanglement property. So any optimization problems, we can make a very big task very simple to very simple due to this optimization concept. So since a qubit can be in the state of both 0 and 1 at the same time, the amount of classical information contained by n qubits is equal to 2 power n. So due to this, quantum computers excel at optimization problems. So they are very skilled at solving problems where there are exponential amount of permutations to try out. So if you find the value of a single permutation for a single system, there is a possibility to find to get the solution for another one permutation for another one system. So this property is called as entanglement property. So the next property is interference property. So interference, so there is a possibility for quantum systems, many simultaneous quantum systems executed parallelly to collide with each other. So interference is the mechanism by which A hypothetical quantum computer would combine its multiple calculations into one answer. So if I will show you with this example. So I have represented ket psi is equal to alpha ket 0 plus beta ket 1. Suppose in that same example, coin example, suppose if you get a tail, so this value will get cancelled. So beta value gets cancelled. Only you will be getting tail with alpha probability. So I have cancelled this beta value. And see the second example. Suppose if I get head. Suppose if I get when I observe the system, I observe a head. So what happens? This tail value gets cancelled. So you'll be getting only the beta value, that is head with some probability. So this property is called as interference. Interference can be used to control the quantum states and amplify the signals. So instead of representing alpha ket 0 plus beta ket 1, the observed value you have written. So amplify the signals that are leading towards the right answer while cancelling signals that are leading towards the wrong answer. So this property is called as interference property. So next we will go on to quantum information. So I explained you about quantum bits, then quantum states, single qubit state and multiple qubit state. Now we'll go on to quantum information. So each see in this diagram, so this is one quantum system, and this blue shaded is one quantum system, and yellow shaded picture is another one quantum system. So how to represent the information? Assume that this quantum system is in a particular state 0, and this quantum state at a particular time is in state 1. So there is a possibility for the quantum state to mix with to have equal value with to have simultaneous value with yellow color picture. So this blue color picture and yellow color picture can have similar values simultaneously. So that I have written like 0 plus 1. So this thing we'll call it as quantum information. So quantum information are represented in the form of ket 0 and ket 1 symbols. So there are two types of quantum information. One is open system, another one is closed system. So there are two cases where quantum information can occur. One is in open system, another one is in closed system. So in an open system, a system that is mixed with the environment, we'll call it as open system. So it's this type of system suffers from noise because it is mixed with the environment. So closed system, a system that is not mixed with the environment and it does not suffer from noise. So the information can be represented in a different way for these open systems and closed systems. So in a closed system, there is no noise. So if n is equal to 2, so if n is equal to 2, a system can be represented, will be having 4 possible states. If n is equal to 2, if the number of binary numbers, that is, if the state of the system is 2. So the system can be represented in 4 different possible states simultaneously. So C0 0 ket 0 0, C1 ket 01, C2 ket 10, C3 ket 11. So all these 4 states are they are combined, superpositioned, and they are linearly represented. They are linearly represented, and they have they are superpositioned. So when you that is all these values are linearly represented. So this state can be represented in the form of summation. Okay, so this is how we'll be representing a closed system, a quantum information in a closed system. They are not having extra noise. Whatever information you are having, you are just producing that information in the form of different states simultaneously. And in an open system, the system is suffering from noise, extra noise. So this is considered, this is a system, rho is a system. So when it is mixed with the environment, it will produce row with it will produce a different state. Consider this is the state. Row is the state of a system. Row is the state of a system, initial state of the system. When it is mixed with an environment, it will produce row dash. So row dash, that is, row is a density operator. An open system we cannot represent simply like a get psi like that. We cannot represent because open system is a combination of mixed values, that is pure state as well as mixed states combined to form a density, that is a combined to form a open system. So such type of open system we cannot represent using normal psi symbols. So we have to use density operators or density matrix row. So what is meant by pure state? So in this example, ket 0, ket 0. So ket that is a ket, the thing the operation of ket is just matrix representation. So this symbol it is used for, it denotes the transpose of this matrix. Okay, so this symbol denotes the transpose of this matrix. So this state, a state that is having the either 0 or 1, we'll call it as pure state. So this is a pure state and this is a another one pure state. So when you combine these two states, when you combine these two states, it becomes a mixed state. It becomes a mixed state. So this type of this type of states can be represented only using density operator. So density operator, using density operator, I can represent a pure state as well as a mixed state. So a closed system, no need any density operator. It does not suffer from noise. So simply we can represent. But an open system, we need to represent it using a density operator only because it has mixed states. Then quantum gates. So the next concept is quantum gates. So a classical computer is built from electrical circuit consisting of wires and logical gates. So similarly, a quantum computer is built from a quantum circuit containing wires and elementary quantum gates to carry around and manipulate the quantum information. So there are two types of gates. First one is single qubit gates and the second one is multiple qubit gates. So there are different types of single qubit gates. So I'm in this webinar, I will be explaining only few, 3 to 4 single qubit gates. Only 4 single qubit gates I will be explaining. The first one is the X gate. So X gate is similar to normal classical NOT gate. So if the input is get 0, the output will be get 1. If the input is get 1, the output will be get 0. So this is how we'll be representing the X gate in vector form. That is get 0, get 1 with alpha beta probabilities is equal to get 0, get 1 with beta alpha probabilities, or get 1, 0 with beta alpha probabilities. So this is how we'll be representing the X gate in the form of a matrix. So this is 1 and this is 0. The next gate is the Y gate, and this gate, that is this gate, if the input is get 0, the output will be I get 1. I get 1. If the input is get 1, the output will be minus I get 0. So how will you represent this gate in the form of a vector? So alpha get 0 with probability alpha, get 1 with probability beta is equal to, that is minus, that is when the input is get 0, you are getting output as I get 1. So get 1. So that's why we have represented as beta. Okay. So the matrix representation. So how will you represent it in the form of a matrix? So 0, I, that is 1 I have represented as 0, I, and 0 I have get 0 I have represented as minus I 0. That is instead of 1 I have written as I. The next thing is Z gate. So Z gate, this gate is used for flipping, that is bit flip operations. we can use this Z gate. So if the input is get 0, the output is get 0. If the input is get 1, the output is minus get 1. So this is how we are representing it in the form of vector representation and matrix representation. So input is get 0. So this is the notation for 0, 1, 0. So this is the notation for get 1. That is, we normally will represent 1 as 1, 0. So input, if the input is get 0, you are getting get 0. If the input is get 1, you are getting minus get 1. So that's why I have written as minus 1, 0, minus 1. The next gate is the Hadamard gate. So this Hadamard gate is finds its application, maximum applications in quantum computing. And suppose if the input is get 0, so there is the possibility of getting get 0 and get 1 with equal probabilities. In such case, we can go for Hadamard gate. So suppose when you want to color a ball, so assume, for example, I want to pass a ball, a plain ball, into a hollow cylinder, and when it is moving through that hollow cylinder, it will be colored, and when it comes out of that hollow cylinder, it will be colored half blue and half red. So the ball is initially it is in state get 0, but when it comes out of the hollow cylinder, it is having equal, that is half of its shape is colored with blue and half of its shape is colored with red. So equal probabilities. So the ball is in two states with equal probabilities. So for such cases, we can go for Hadamard gate. So this is the symbol. If the input is get 0, you'll be getting 1 by root 2 0 get 0 plus get 1. And if the input is get 1, you'll be getting 1 by root 2 get 0 minus get 1. So this is the matrix representation. And this is the vector notation of Hadamard gate. So the next concept is multiple qubit gates. Multiple qubit gates. And one of the multiple qubit gate is C0 gate, that is controlled NOT gate. So it is similar to generalized XOR gate. And here C0 gate takes two inputs because inputs should be more than 2 or more than 2. So C0 gate takes two inputs, A and B, and these two inputs are will be giving an output like A, B XOR A, B XOR A. So here I have taken two inputs, 0 and 1 are the two inputs. So when the state is 0, 0, when the inputs are in, when the system is in state 0, 0, get 0, 0, you will be getting get 0, 0, no problem. 0, B XOR A, you will be getting 0, 0. So if the input is get 0, 1, you will be getting get 0, 1. If the input is get 1, 0, so there is a change. If the A value changes, there will be if the A value changes, there will be a change in the output. So get 1, 0, the output will be get 1, 1. And if the input is get 1, 1, the output is get 1, 0. And this is the matrix representation of C0 gate. C0 gate is a unitary quantum gate. So unitary quantum gate means, so represent a particular this matrix and gate in matrix form. So when you take the transpose of this matrix, so you will be getting a unit value. Unit value will be getting. So this type of matrix will be called as unitary quantum gate. When you reverse, when you take transpose also, you'll be getting a value of 1 unit value. So that's why these gates are called. This gate is called as unitary quantum gate. And the next gate is controlled U gate. So controlled U gate, it is a multiple qubit gate. So this gate can be finds most of its applications in quantum phase estimation. Suppose if you want to consider that a balloon or something is moving in the open air, mid-air, or a coin, you can tell a system is in mid-air. Suppose I want to measure the state of phase of that particular system. So in such case, we can go for controlled U gate. So the input is, if the C stands for control bit, the T stands for target bit. So these are the two inputs. So if the If the input is, these two inputs can be represented in 4 different ways. States simultaneously can occur, these states can occur simultaneously. And if the input is get 0, 0, the output will be get 0, 0. That is C is doing having one unitary operation U power C. U power C. It is going. It will be. It is having. It is doing a tensor product operation on T. So if the input is get 0, 0, output is get 0, 0. If the input is get 0, 1, output is get 0, 1. If the input is get 1, 0, the output is. So if the control bit changes, so here the control bit is changed 1, 1, 0. So the output will be get 1 tensor product. This product is called, this operator is called as tensor product unitary operation on 0, on get 0. And that is equal to 1 get 1 tensor product, get 1 tensor product. So this what does this u get 0 symbol do? So this operator will be doing this operation u 0, 0 get 0, u 1, 0 get 1. That is will be multiplying 1 with 0, then 1 with 1, like that you will be get 1 with 0, get 1 with 1, like that you will be multiplying. And this is the matrix representation of control U gate. Control U gate. And so next, the next very important topic is quantum computing applications. So quantum computing has a lot of applications. In machine learning, we can use this quantum computing concepts to search. Suppose we are having a very large database or a very big data. So I want to search a particular value, that is a variable that is having a particular value. So we can go for quantum computing algorithms. There are searching algorithms, quantum searching algorithms we have. Then the next application is quantum, that is computational chemistry. In computational chemistry, we can apply this quantum computing concepts, that is fertilizers, to choose which fertilizer, how to choose equal proportion of fertilizers for a particular land, land. All these things for a particular crop, to grow a particular crop, which there are different fertilizers available. How to choose equal proportion of the fertilizers. So all these things can be applied using quantum computing concepts. So how to set the room temperature for a particular room, how to set the room temperature. So how to add equal proportion of chemicals for creating a new battery. So all these things, for doing all these things, we can go for quantum computing. And third thing, financial portfolio optimization. So it is used for that is before you apply, before you try for a particular implement a particular product, you are doing simulations and checking whether it will work or not. Because after developing, if it didn't work, it will cause a lot of loss. So before that, you're doing simulations using quantum algorithms. Then logistics and scheduling, how to schedule tasks and service them for better profit with customer satisfaction. Then drug design. So I want to create a drug. Then how to, so before creating a drug, I am simulating and checking whether this drug will work for this particular crop or fertilizer or for this particular sickness. So in drug design, quantum computing is very much applicable. Cyber security. So how to recognize the threats earlier and mitigate the damage that they may do. Like how to create non-breaking keys. So how to create a cryptographic keys so that they cannot be breakable. So can be applied using quantum computing. And code breaking. And circuit, software, and system fault simulation. So before developing a system, you can simulate and check that system whether it will work or not. Then optimization. Many optimization problems, we can apply this quantum computing. Entanglement property. Then this is another one application, quantum phase estimation. I have just projected the problem alone. So in which for which type of problem we can apply this quantum phase estimation. So given a unitary operator U, the algorithm, I want to find phase, that is theta. I want to find theta in a particular system. So when the system mixed with a unitary operation, so it will be yielding another one system with some eigen values. So from this eigen value, how will I find the phase of that particular system, in which position it is? So all these things can be applicable using quantum phase estimation algorithm. Then quantum searching. So this is another one application where, for example, that in a big data or in a very large database, you want to find a particular variable whose value is this particular value. I want to find a variable with which matches a particular value. So in such case, we can apply this quantum searching algorithm. Normally, using classical computing, this algorithm takes an order of n times complexity. But using quantum search algorithms, it will take order of root n. That is a very common, well-used algorithm. That is Grover's quantum search algorithm. So this algorithm takes order of root n to search a particular value in a database variable. The next application is quantum counting. That is, suppose you assume that there is a list of problems to be solved, and there are a lot of solutions also available. So how to choose the exact solution, correct solution for this particular problem can be achieved using quantum counting algorithms. Then the next application is quantum error correction. So normally in classical error correction, how will you correct an error? You will be adding to the original bit, you'll be adding some redundant bits, and then you'll be checking for then you'll be doing error correction. But in quantum error correction, you will not be doing adding any redundant bits. You'll be using a non-cloning theorem. It is using a non-cloning theorem. Then in classical error correction, the errors can be determined and corrected, and the error correction is a discrete process. But in quantum error correction, the errors cannot be determined, and still research is going on in this area. And the error correction is a very continuous process. And in classical error correction, errors can be detected and recovered. The original lost data can be recovered. But in quantum error correction, the lost data cannot be encoded after, it cannot be decoded successfully. So a lot of research is going on in this area. You can also try in this area if you are willing to do this quantum error, do research in this area. So we learned about quantum concepts, quantum computing concepts, qubits, then states, quantum states. Then we learned about the quantum information. Then quantum information in a closed system and open system. Then quantum gates will I explained you. Then I explained you about the applications of quantum computing, and this is all about quantum computing. Still more topics are left out, so I think this much is enough for this section, and I thank you. And if you have any queries, you can kindly post on this chat window so that I can answer you. And I thank you very much. And I especially thank Professor Dr. R. Ravi sir, Department of IT, Francis Xavier Engineering College, Tirunelveli, Tamil Nadu, for providing me an opportunity to present in this webinar on this specified topic. Thank you. Thank you, sir.